I am Ashwini Kumar, Assistant Professor, Department of Electronics and Communication Engineering, Babu Banarsi Das University, Lucknow.
In this session, we are going to discuss about the baseband demodulation or detection. Let us start with the signals and noise. Error performance degradation in communication systems. The task of the detector or demodulator is to retrieve the bit stream from the received waveform as error-free as possible. Notwithstanding the impairments to which the signal may have been subjected, there are two primary causes for error performance degradation. The first is the effect of filtering at the transmitter, channel and receiver, which is called as a non-ideal system transfer function, causes symbol smearing or inter-symbol interference, ISI. This we have already discussed in my first video. This we have already discussed in my earlier videos. Another cause for error performance degradation is electrical noise and interference produced by a variety of sources such as galaxy and atmospheric noise, switching transients, intermodulation noise, as well as interfering signals from other sources. With proper precautions, much of noise and interference entering a receiver can be reduced in intensity or even eliminated. However, there is one noise source that cannot be eliminated, and that is the noise caused by the thermal motion of electrons in any conducting media. This motion produces thermal noise in amplifiers and circuits and corrupts the signal in additive fashion. The primary statistical characteristics of thermal noise is that the noise amplitudes are distributed according to a normal or Gaussian distribution that we have discussed in my earlier video. It can be seen that most probable noise amplitudes are those with small positive or negative values. In theory, the noise can be infinitely large, but very large noise amplitudes are rare. The primary spectral characteristics of thermal noise in communication system is that its two-sided power spectral density GNF, which is equals to N0 by 2, is flat for all frequencies of interest. In other words, the thermal noise on the average has just as much power per hertz in low frequency fluctuations as in high frequency fluctuations, up to a frequency of about 10 to the power 12 hertz. Up to a frequency of about 10 to the power 12 hertz. When the noise power is characterized by such a constant power spectral density, we refer to it as white noise. We have already discussed about AWGN. Since thermal noise is present in all communication system and is the predominant noise source for many systems, the thermal noise characteristics additive, white and Gaussian, giving rise to the name AWGN, are most often used in model the noise in the deletion process, are used to model the noise in the detection process and in the design of receivers. Whenever a channel is designated as an AWGN with no other impairments specified, we are in effect being told that its impairments are limited to the degradation caused by the unavoidable thermal noise. Now come to demodulation and detection. Is there any difference between demodulation and detection? Let us see. During a given signaling interval T, a binary baseband system will transmit one of two waveforms, that is G1T and G2T. Similarly, a binary bandpass system will transmit one of two waveforms denoted by S1T and S2T. Since the general treatment of demodulation and detection are essentially the same for baseband and bandpass systems, we use SIT here as a generic designation for a transmitted waveform. Whether the system is baseband or bandpass, this allows much of the baseband demodulation or detection treatment. This allows much of the baseband modulation detection treatment in this chapter to be consistent with the similar description that we have discussed. Then for any binary channel, the transmitted signal over a time over a simple period 0t is represented by SIT is equal to S1t for one interval 0 to t for binary 1 and S2t between 0 to t for a binary 0. The received signal RT degrades by noise NT and possibly degraded by the impulse response of the channel, that is HCT, which is given as RT is equal to SIT convolution HCT plus NT. I can be 1 to M. Here NT is assumed to be 0 mean AWGN process and star means convolution operation. For binary transmission over an ideal distortionless channel where convolution HCT produces no degradation, the representation of RT can be simplified to RT equal to SIT plus NT. Now the figure, we're talking about this figure. This figure shows the typical demodulation and detection functions of a digital receiver. We define demodulation as recovery of a waveform to an undistorted baseband pulse, and we designate detection to mean the decision-making process of selecting the digital meaning of that waveform. If error correction coding not present, the detector output consists of estimates of message signals, message symbols or bits, MEC, also called hard decisions. If error detection coding is used, the detector output consists of estimates of channel symbols, UICAP, which can take the form of hard or soft decision. For brevity, the term detection is occasionally used loosely to encompass all the receiver signal processing which steps through the decision making step. The frequency down conversion block in this figure, I am talking about this figure, this block performs frequency translation for bandpass signals operating at some radio frequency RF. This function may be configured in a variety of ways. It may take place within the front end of the receiver, within the demodulator, shared between two locations, or not at all. Within the demodulator, within the demodulate and sample block, within the demodulate and sample block, the receiving filter which performs waveform recovery in operation for the next important step, detection. The filtering at the transmitter and the channel typically cause the received pulse sequence to suffer from ISI, and thus it is not quite ready for sampling and detection. The goal of the receiving filter is to recover a baseband pulse with the best possible signal to noise ratio, free of any ISI. The optimum receiving filter for accomplishing this is called a matched filter or correlator, that we will see in later slides. An optional equalizer follows the receiving filter. It is only needed for those systems where channel induced ISI can distort the signals. The receiving filter and equalizing filter are shown as two separate blocks in order to emphasize their separate functions. This is the equalizing filter and this is the receiving filter. These two filters are separated. In most cases, however, when an equalizer is used, a single filter would be designed to incorporate both functions and thereby compensate for the distortion caused by both the transmitter and the channel. Such a composite filter is sometimes referred to as the equalizing filter or the receiving and equalizing filter. The above figure highlights two steps in the demodulation or detection process. The step 1, the waveform to sample transformation is made up of demodulator followed by a sampler. At the end of each symbol duration t, the output of the sampler, the pre-detection point, yields a sample ZT, sometimes called the test statistic. ZT has a voltage value directly proportional to the energy of the received symbol and inversely proportional to the noise. Step 2, a decision is made regarding the digital meaning of that sample. We assume that the input noise is a Gaussian random process and that the receiving filter in the demodulator is linear. A linear operation performed on a Gaussian random process will produce a second random process. Thus the filter output noise is Gaussian. The output of step 1 yields the test statistics as ZT is equal to AIT plus N0T, I equals to 1 and 2, where AIT is the desired signal component and N0T is the noise component. To simplify the notation, sometime equation this is in the form of Z equal to AI plus N0. The noise component N0 is a zero mean Gaussian random variable, and hence ZT is a Gaussian random variable with a mean of either A1 or A2, depending on whether a boundary 1 or boundary 0 was sent. The PDF of the Gaussian random noise N0 can be expressed as that we have already studied. PN0 is equal to 1 by sigma 0 under root 2 pi exponential of minus half N0 by sigma 0 whole square, where sigma 0 square is the noise variance. Thus it follows from equation this and this. The conditional PDFs PZS1 and PZS2 can be expressed as PZS1 will be equal to 1 by sigma 0 under root 2 pi exponential minus half Z minus A1 upon sigma 0 whole square, and PZS2 is equal to 1 by sigma 0 under root 2 pi exponential minus half Z minus A2 upon sigma 0 whole square. These conditional PDFs are shown below. The rightmost conditional PDF is PZ S1, called the likelihood of S1. Illustrate the probability density function of the random variable ZT, given that symbol S1 was transmitted. Similarly, the leftmost conditional PDF PZS2 is called the likelihood of S2. Illustrates the PDF of ZT when the symbol S2 was transmitted. The abscissa ZT represents the full range of possible sample output values. After a received waveform has been transformed to a sample, the actual sample of the waveform is no longer important. All waveform types that are transmitted to the same value of ZT are identical for detection process. Later it will be shown that optimum receiving filter or match filter, which we will be using in step 1 of the above figure, maps all signals of equal energy into the same point ZT. Therefore, the received signal energy, not its shape, is the important parameter in the detection process. That is why the detection analysis for baseband signal is same as that for bandpass signal. Since ZT is a voltage signal that is proportional to the energy of the received symbol, the larger the magnitude of ZT, the more error free will be the decision making process. In step 2, detection is performed by choosing the hypothesis that results from the threshold measurement. That is ZT greater than or equal to H1 first hypothesis and H2, and gamma will be the threshold value. H1 and H2 are two possible hypotheses. The inequality relationship indicates that hypothesis H1 is chosen if ZT is greater than threshold value gamma. The hypothesis H2 is chosen if ZT is less than gamma. If ZT equal to gamma, the decision can be an arbitrary one. Where H1 and H2 are two possible binary hypotheses. The inequality relationships indicate that hypothesis H1 is chosen if ZT is greater than gamma, and hypothesis H2 is chosen if ZT is less than gamma. But if ZT equals to gamma, the decision can be an arbitrary one. Choosing H1 is equivalent to deciding that signal S1T was sent and hence a binary 1 is detected. Similarly, choosing H2 is equivalent to detecting that signal S2T was sent and hence a binary 0 is detected. Since ZT is a voltage that is proportional to the energy of the received symbol, the larger the magnitude of ZT, the more error free will be the decision making process. In step 2, Detection is performed by choosing the hypothesis that result from the threshold measurement. Zt is greater than H1, less than H2 gamma, where H1 and H2 are two possible binary hypotheses. The inequality relationship indicates that hypothesis H1 is chosen if Zt is greater than gamma. Hypothesis H2 is chosen if Zt is less than gamma. However, if Zt equals to gamma, the decision can be an arbitrary one. Choosing H1 is equivalent to detecting that signal S1T was sent and hence a binary 1 is detected. Similarly, choosing H2 is equivalent to detecting that a signal S2T was sent and hence a binary 0 is detected. Now come to variance of white noise. White noise is an idealized process with two-sided power spectral density equal to a constant n0 by 2 for all frequencies ranging from minus infinity to plus infinity. Hence the noise variance average noise power, since the noise has zero mean, is defined as sigma square will be equal to variance of noise nt, that is equal to integration minus infinity to plus infinity n0 by 2 df, which is equal to infinity. Although the variance for AWGN is infinite, the variance for filtered AWGN is infinite. For example, if AWGN is correlated with one of a set of orthogonal functions psi jt, the variance of the correlator output is given by sigma square equals to variance nj equal to E expectation or ergodic, sigma square equal to VAR, sigma square equal to variance nj equal to E integration 0 to t nt psi j t dt whole square will be equal to n0 by 2. Now variance of white noise. White noise is an idealized process with two-sided power spectral density equal to constant n0 by 2 for all frequencies ranging from minus infinity to plus infinity. Hence the noise variance average noise power, since the noise has zero mean, is given as sigma square equal to variance of nt is equal to integration minus infinity to infinity n0 by 2 df will be equal to infinity. Although the variance for AWGN is infinite, the variance for filtered AWGN is finite. For example, if AWGN is considered with one of the set of orthonormal functions sigma j_t, the variance of the correlator output is given by sigma square equal to variance nj equal to E of 0 to integration 0 to t nt psi j t dt whole square, which is equal to n0 by 2. The basic SNR parameter for digital communication systems. Anyone who has studied analog communication is familiar with the figure of merit average signal power to average noise power ratio. In digital communication, we more often use EB by N0, a normalized version of SNR, as a figure of merit. EB is the bit energy and can be described as signal power S times the bit time dB. N0 is noise power spectral density and can be described as noise power N divided by bandwidth W. Since the bit time and bit rate RB are reciprocal, we can replace TB with 1 by RB, and so we get EB by N0 is equal to S into TB upon N by W, which is equal to S by RB equal to N by W. Data rate in units of bits per second is one of the most recurring parameters in digital communication. We therefore simplify the notation throughout the above equation. Emphasize that EB N0 is just a version of signal to noise normalized by bandwidth and bit rate as follows. EB by N0 is equal to S by N W by R. One of the most important metrics of performance in digital communication system is a plot of the bit error probability PB versus EB by N0, which is shown in the below figure. Here we can see plot is between EB by N0 and PB. This is the general shape of the PB versus EB N0 curve. So the below figure illustrates the waterfall like shape of most such curves. For EB by N0 greater than equal to R0 and PB is less than equal to P0, the dimensionless ratio EB by N0 is standard quite is a standard quality measure for digital communication system performance. Therefore, required EB by N0 can be considered a metric and characterizes the performance of one system versus another. The smaller the required EB by N0, the more efficient is the detection process for a given probability of error. Now we will discuss why EB by N0 is a natural figure of merit. A novice person to digital communication may question the usefulness of the parameter EB by N0. After all, signal to noise ratio is a useful figure of merit for analog communication. The numerator represents a power measurement of the signal we want to preserve and deliver, and the denominator represents electrical noise degradation. Moreover, signal to noise ratio is intuitively acceptable as a metric of goodness. Thus, why cannot we continue to use signal to noise ratio as a figure of merit for digital communication? Why is a different metric for digital system? The ratio of bit energy to noise per spectral density is taken. Earlier we have studied that a power signal was defined a signal having finite average power and infinite energy. An energy signal was defined as a signal having zero average power and finite energy. These classifications are useful in comparing analog and digital waveforms. We classify an analog waveform as power signal. Why does this make sense? We can think of an analog waveform as having infinite duration that need not be partitioned or windowed in time. An infinitely long electrical waveform has an infinite amount of energy. Hence, energy is not a useful way to characterize this waveform. Power or rate of delivering the energy is a more useful parameter for the analog waveforms. However, in a digital communication system, we transmit and receive a symbol by using a transmission waveform within a window of time. The symbol time Ts. Focusing on one symbol, we can see that power average over all time goes to 0. Hence, power is not a useful way to characterize digital waveform. What we need for such waveform is a metric of the good stuff within the window. In other words, the symbol energy is a more useful parameter by characterizing digital waveforms. The fact that a digital signal is best characterized by its received energy doesn't yet get to the crux of why EB by N0 is a natural metric for digital system. So let us continue. The digital waveform is a vehicle that represents a digital message. The message may contain 1 bit, 2 bits or 10 bits. In analog system, there is nothing akin to such a discrete message structure. An analog information source is an infinitely quantized continuous wave. For digital system, a figure of merit should allow us to compare one system with another at the bit level. Therefore, a description of the digital waveform in terms of signal to noise ratio is virtually useless, since the waveform may have a 1 bit meaning, a 2 bit meaning or a 10 bit meaning. But for example, suppose we are told that for a given error probability, the required signal to noise ratio for a digital waveform is 20 units. We can think of waveform as being interchangeable with its meaning. Since the binary waveform has a 1 bit meaning, then the signal to noise ratio requirement per bit is equal to the same 20 units. However, suppose that the waveform is 1024 array with the same 20 units of required signal to noise ratio. Now, since the waveform has a 10 bit meaning, the signal to noise ratio requirement per bit is only 2 units. Why should we have to go through such computational manipulations to find a metric that represents a figure of merit? Why not immediately describe the merits in terms of what we need? An energy related parameter at the bit level EB by N0. Just as signal to noise ratio is a dimensionless ratio, so as EB by N0. To verify this, consider the following units of measurements. Here we see that both EB and N0 will have the same unit. Now come to the detection of binary signals in Gaussian noise. Maximum likelihood receiver structure. The decision making criterion shown in step 2 of figure 3.1 that we have already studied was described by equation 3.7. We know about this equation. where H1 was one hypothesis, H2 was another one, and we decided which symbol was sent according to these hypotheses. A popular criterion for choosing the threshold level gamma for the binary decision in equation 3.7 is based on minimizing the probability of error. Popular criterion for choosing the threshold level gamma for the above equation is based on minimizing the probability of error. The computation for this minimum error value of gamma equals to gamma 0 starts with the forming an inequality expression between the ratio of conditional probability density functions and signal a priori probabilities. Since the conditional density function Pz Si is also called the likelihood of S1. The formulation, I am talking about this formulation, Pz S1 upon Pz S2 greater than equal to H1 and H2 PS2 by PS1 is called the likelihood ratio test. In this inequality, PS1 and PS2 are the a priori probabilities that S1t and S2t respectively are transmitted, and H1 and H2 are two possible hypotheses. The rule for minimizing the error probability state that we should choose hypothesis H1 if the ratio of the likelihood is greater than the ratio of a priori probabilities. Equation of 3.5 and 3.6. The substitution of equation 3.5 and 3.6 into 3.31, we get that Zt is equal to A1 plus A2 by 2 equal to gamma 0, where A1 is the signal component of Zt when S1t is transmitted and A2 is the signal component of Zt when S2t is transmitted. The threshold level gamma 0 represented by A1 plus A2 by 2 is a optimum threshold for minimizing the probability of making an incorrect decision for the important special case. This strategy is known as minimum error criterion. For equally likely signals, the optimum threshold gamma 0 passes through the intersections of the likelihood function as shown in the figure 3. As shown in this figure. Thus, by following equation 3.32, this equation, the decision strategy effectively selects the hypothesis that corresponds to the signal with maximum likelihood. For example, given an arbitrary detector output Z0t, Zat for which there is a non-zero likelihood, and Zat belongs to the either signal class S1t or S2t, one can think of the likelihood test as a comparison of likelihood values of Pz A S1 or Pza S2. The signal corresponding to the maximum PDF is chosen so as the most likely to have been transmitted. In other words, if detector choose S1t, if Pza S1 is greater than Pza S2. Otherwise, the detector chooses S2t. A detector that minimizes the error probability is known as the minimum likelihood detector. The figure of PDF that we have already seen illustrate this equation is just a common sense way to make a decision when there exists statistical knowledge of the classes. Given the detector output as Zat that we have already seen in the figure, Zat intersects the likelihood of S1t at a value L1 and it intersects the likelihood of S2t at a value of L2. Here we see at value L1 and this is the value L2. Level L1 and then L2. What is the most reasonable decision for the detector to make? For this example, choosing class S1t, which has the greater likelihood, is the most sensible choice. If this was an M array instead of binary example, there would be a total of M likelihood functions representing the M signal classes to which a received signal might belong. The maximum likelihood decision would then be to choose the class that had greatest likelihood of all M likelihoods. Now come to error probability. For the binary decision making, which was depicted in figure 3.2, there are two ways errors can occur. An error E will occur when S1t is sent and channel-wide results in the receiver output signals Zt being less than gamma 0. The probability of such an occurrence is PES1 equal to PH2S1 will be equal to Integration of minus infinity to gamma 0 pzs1 dz. It is illustrated by the shaded area of the figure. This is illustrated by the shaded area to the left of gamma 0 in the figure. That is, we are talking about this region, minus lambda 0 to lambda 0, this region. And for another case, integration will be from plus infinity to this gamma 0. Similarly, an error occurs when S22 is sent and the channel noise results in ZT being greater than gamma 0. The probability of this occurrence is PES2 is equal to PH1S2 will be equal to gamma 0 to plus infinity PZS2 dz. The probability of an error is the sum of the probabilities of all the ways that an error can occur. For the boundary case, we can express the probability of bit error as PB is equal to sigma I equals to 1 to T P function of E and SI equals to I equal to 1 sigma PESI into PSI. Combining about two equations 3.4 and 3.6, this equation and this equation we are combining, then we can write PB equal to PES1 PS1 plus PES2 PS2, or equivalently we can say PB equal to PH2 S1 PS1 plus PH1 S2 into PS2. That is, given that signal S1T was transmitted, an error results if hypothesis H2 is chosen, or given that signal S2T was transmitted, an error results if hypothesis H1 is chosen. For the case where a priori probabilities are equal, that is PS1 equal to PS2 is equal to half, PB will become as half, PB will be equal to 1 by 2 H2 upon S1 plus 1 by 2 PH1 S2. And because of the symmetry of the probability density function, PB will be equal to PH2 S1 or PH1 S2. The probability of bit error PB is numerically equal to the area under the tail of the likelihood function PZ1 or PZ2 falling on the incorrect side of the threshold, as we can see in the figure, as we can see in this figure. We are talking about this region. We can therefore compute PB by integrating PZS1 between the limits of minus Z and gamma 0, or by integrating PZS2 between the limit gamma 0 and infinity. So PB will be equal to gamma 0, that will be equal to A1 plus A2 by 2 to infinity PZS2 dz. Here gamma 0 equal to A1 plus A2 by 2 is optical threshold. Replacing the threshold with the Gaussian equivalent from equation, we have PB equal to gamma 0 equal to A1 plus A2, PB equal to integration gamma 0 equal to A1 plus A2 by 2 to infinity 1 by sigma 0 under root 2 pi exponential of minus of Z minus A2 by sigma 0 whole square dz, where gamma 0 is the variance of the noise out of the correlator. Let A equal to Z minus A2 upon sigma 0, then sigma 0 du equal to dz, and we get PB equal to u equal to A1 minus A2 upon 2A0 and other limit u equal to infinity 1 by under root 2 pi exponential of minus, we get PB equal to integration of u equal to A1 minus A2 to sigma 0 and u equal to infinity 1 by under root 2 pi exp exponential minus u square by 2 du will be equal to q function A1 minus A2 upon 2 sigma 0, where qx is called the complementary error function or co-error function. Is commonly used symbol for the probability under the tail of the Gaussian PDF. It is defined as qx equal to 1 by root 2 pi integration x to infinity exponential of minus u square by 2 du. The co-error function is defined in several ways, where qx called the complementary error function or error function is a commonly used symbol for the probability under the tail of the Gaussian PDF. It is defined as qx equal to 1 by root 2 pi integration x to infinity exponential minus u square to du. Now come to the matched filter. A matched filter is a linear filter designed to provide a maximum signal to noise power ratio at its output. Now come to the matched filter. A matched filter is a linear filter designed to provide a maximum signal to noise power ratio at its output for a given transmitted symbol waveform. Consider that known signal xt plus awgn and t is the input to a linear time invariant receiving filter followed by a sampler. At time t equal to t, the sampler output zt consists of a signal component ai and a noise component n0. The variance of the output noise is denoted by sigma 0 square, so that the ratio of the instantaneous signal power to average noise power at a time t equal to t out of the sampler in step 1 is given as s by n t ai square by sigma 0 square. We wish to find the filter transfer function h0f that maximizes the equation 3.45. We can express the signal ait at the filter output in terms of the filter transfer function hf and the Fourier transform of the input signal as ait is equal to integration minus to infinity to plus infinity hf sf e to the power j 2 pi ft df, where sf is the Fourier transform of the input signal st. If the two-sided power spectral density and the input noise is n0 by 2 watts per hertz, then we can use equation 3.19, 1.19 and 1.53. Density of the input noise is n0 2 watts per hertz. Then we can express the output noise power as sigma 0 square equals to n0 by 2 integration minus infinity to plus infinity hf square df. Now we can combine these two equations, this 3.45 and 3.46 and 3.47, to express signal to noise ratio t as follows. S and t will be equal to sigma of integration minus infinity to plus infinity hf sf e z 2 pi ft df whole square divided by n0 by 2 integration minus infinity to plus infinity hf square df. We next find that value of hf equal to h0f, for which the maximum s by n t is achieved by using Shor's inequality. One form of the inequality can be stated as mod of integration minus infinity to plus infinity f1x into ftx whole square is less than or equal to integration minus infinity to plus infinity fx1 square dx and integration minus infinity to plus infinity f2x square dx. The equality holds if f1x is equal to k f2 star x, where k is an arbitrary constant and a star dictates the complex conjugate. If we identify hf with f1x and sf e j2 pi ft with f2x, we can write mod of integration minus infinity to plus infinity hf sf e j2 pi ft df whole square less than equal to integration minus infinity to infinity hf square df. Integration of minus infinity to infinity, integration of minus infinity to infinity sf whole square df. Now we can substitute this result into equation this 3.48. Then we get s by nt less than equal to 2n0 integration minus infinity to plus infinity sf square df, or max sn by t equal to 2e by n0, where the energy E of the input signal st is given by E equal to integration between minus infinity to plus infinity sf square df. Thus the maximum Sn by t depends on the input signal energy and the power spectral density of the noise, not on the particular shape of the waveform that is used. The equality in this equation, that is 3.52, holds only if the optimum filter transfer function h0f is employed, such that hf equal to h0f equal to k s star f e to the power minus j 2 pi f t, or ht equal to inverse Fourier transform ks conjugate f e to the power minus j 2 pi f t. Since st is a real valued signal, we can write from equation, since st is a real valued function, we can write, since st is a real valued signal, we can write ht equal to kst minus t between interval 0 to t and 0 elsewhere. Thus the impulse response of the filter that produces the maximum output signal to noise ratio is the mirror image of the message signal S. Thus the impulse response of the filter that produces the maximum output signal to noise ratio is the mirror image of the signal St, delayed by the symbol time duration t. Here we note that delay of t seconds makes the equation causal. That is, the delay of t seconds make ht a function of positive times in the interval that is between 0 to t. Without the delay of t seconds, the response s minus t is unrealizable because it describes a response as a function of negative time. Now come to the correlation realization of the matched filter. Now come to correlation realization of the matched filter. The above equation and figure, I am talking about this figure, illustrates the matched filter's basic property that we will see shortly. The impulse response of the filter is delayed version of the mirror image rotated on the t equals to 0 axis of the signal waveform. Here we can say the signal waveform and this is a mirror image of the signal waveform and impulse response of the matched filter. Therefore, if the signal waveform is st, its mirror image is s minus t and the mirror image delayed by t seconds is st minus t. The output zt of a causal filter can be described in time domain as the convolution of a received input waveform rt with the impulse response of the filter. That is zt equal to rt convolution ht, which is equal to integration 0 to t h r tau h t minus tau d tau. Substituting ht of equation 3.56 in above equation into ht minus tau, we get zt is equal to integration of 0 to t r tau s t minus tau d tau, that is 0 to t r tau s t minus tau plus tau d tau, where t equals to t. Then now we can write this equation as zt equal to 0 to t r tau s tau d tau. This equation, the operation of this equation, the product integration of the received signal rt with the replica of transmitter signal st over one symbol interval is known as the correlation of rt with st. Consider that a received signal rt is correlated with each prototype signal sit I equals to 1 to m, making a bank of m correlators. The signal sit whose product integration or correlation with rt yields the maximum output zit is the signal that matches rt better than all the other signal as j is not equal to I. We will subsequently use this correlation characteristic for the optimum detection of the signals. Now we can compare the convolution and correlation. The mathematical operation of a matched filter is convolution. A signal is convolved with the impulse response of the filter. The mathematical operation of correlator is correlation. A signal is correlated with replica of itself. The term matched filter is often used synonymously with correlator. How is that possible when their mathematical operations are different? Recall that the process of convolving two signals results one of them in time. Recall that the process of convolving two signals reverses one of them in time. Also, the impulse response of an matched filter is defined in terms of a signal that is reversed in time. Thus, convolution in the matched filter with a time reverse function results in second time reversal, making the output appear to be the result of a signal that has been correlated with its replica. Therefore, it is valid to implement the receiving filter in figure 3.1 with either a matched filter or a correlator. It is important to note that the correlator output and the matched filter output are the same only at a time t equal to t. For a sine wave input, the output of the correlator zt is approximately a linear ramp during the interval 0 to t. However, the matched filter output is approximately a sine wave that is amplitude modulated by a linear ramp during the same time interval. The comparison is shown in figure 37b. Since for comparable input, the matched filter output and the correlator outputs are identical in sampling time t equals to t. The matched filter and correlator functions Pictured in figure 3 are often used interchangeably. In this figure, they are going to be used interchangeably. The first is the mat filter and second is the correlator. And when we are comparing, we are talking about these two comparison. This is the correlator output and this is the matched filter output.